wanted to have this little fika here about artificial intelligence because there's a lot of misconception of what exactly artificial intelligence is and how exactly it began and everything. A lot of people see self-driving cars and they say, okay, this is artificial intelligence. But artificial intelligence is it's a vast field, and it encompasses a lot of different areas, including cognitive sciences and logic and philosophy and mathematics. And basically, this is a small historical overview, along with some other examples, basically, of what exactly we can do with artificial intelligence and what has been done in the past. So, early beginnings, I'm going quite far away now. In ancient Greece, there were two different philosophies. One was created by Aristotle. It's called term logic. This is all based on mathematical logic. Aristotle said, for example, he used this logic that, let's say, all men are mortals, all Socrates are men, so all Socrates are mortals. You could say something like that. It's a logical way of saying something. You could also say all ducks are white. Reuben is logic. Then we also had Stoic logic, which was firstly done by Chrysippos. He used if-then, basically. So he says, if it is day, it is light, let's say. But it is not case that it is light. Therefore, it is not the case that it is day. These are two different logical assumptions. The dominant logic was Stoic. That's where Stoic philosophy comes from also. But it was forgotten after antiquity, and Aristotle's logic became more dominant. And then later it was revived. And guess where?
Is it breaking up only for me?
Yeah, me too.
Okay. Tolis, it looks like you are breaking up sometimes. Now I can see the connection is a little bit red. So
just at the time when you said something about the Reuben, and it's like, boom.
Yes, when you're gonna talk terribly about me, then I press the button and kill.
That's the artificial intelligence.
That's why nobody laughed at my joke.
Yeah, because we didn't hear it.
Exactly. You can repeat it.
Okay, so like I said, with Aristotle, you can say all ducks are white. Reuben is white. So Reuben is a duck, right? That's the way. Okay. So I'll continue. So the 20th century. In the 20th century, we have, of course, a revival of mathematical logic, which led directly to Alan Turing's theory of computation, as you know. Alan Turing is the father of computer science, let's say, and also considered the father of artificial intelligence. Alan Turing has created the Turing machine, which is basically a machine that it's a very simple computer. Basically, it's able to complete any algorithm given to it in a finite amount of time. So any machine that basically can do this, can complete a mathematical algorithm in a finite amount of time, is said to be Turing complete. All of course, modern computers are Turing complete. And also this person, McCulloch and Pitts, these two people, basically they designed Turing complete artificial neurons. Basically, that was the first attempt to create neurons that would be, could solve algorithms, basically, mathematical algorithms. The golden age of artificial intelligence began in the 50s. There was a lot of prominent research. Computers were able to solve checkers. There was also voice-to-text speaking, and they were also able to solve word problems, not word problems, in algebra and logical problems. Am I still breaking up?
No, you're audible. It's going really good.
Okay, and there was a lot of funding by governments, so that was they were able to do a lot of research and a lot of different stuff. It was the beginning of basically people had fantasies of robotic entities that could do a lot of stuff. We still have, of course, these science fiction ideas and stuff like that. So everything then was theory. Of course, programming languages were still procedural. They are based on mathematical notations. One of the first programming languages was Lisp, which was based on like logic also, and it was used for programming artificial intelligence. It's one of the oldest languages along with Fortran. And so you see that artificial intelligence really began along computer science as a science in general, alongside it. And then we had, of course, back in the 80s, there were expert systems. I will talk about this a bit later. So research examples of the golden age. For example, Marvin Minsky, he created like a thesis about how the brain works, basically. So he stipulated that the brain is part of different interconnected mini societies, basically. That's why he called it the society of mind, basically. So let's say that we have different agents like this, but they're actually based in a bureaucracy, like shown in this, and they all interact with each other, and they create an output, basically. This was, of course, very theoretical. So in the 80s, there were expert systems. So this is basically databases that you were able to ask questions, and they were able to ask you a question back, and then finally get to a medical, a diagnosis, not a medical, and any basically topic. So this is an example. This is actually a funny example. So do you feel pain? Yes. Where do you feel pain? Everywhere. Do you feel pain all the time? Whenever I poke myself. So the diagnosis, you have a broken finger. That's a joke, of course.
Good one.
Thanks. But jokes aside, expert systems were designed, of course, to solve complex problems. For example, we have this example with there's a specific rule. Let's say if the lawn is shaggy and the car is dirty, and you mow the lawn and you wash the car, you get $20. So then it works. It asks these questions, and asks more questions, and then it can tell you, okay, if you get $20 or not. Yeah, it's a simple, but still it can become more complicated if you want. And most of these methods were programmed again using Lisp. Of course, Lisp has evolved from the 50s, right? So, for example, this is a small example of Lisp, how to calculate the factorial. As you can see, recursion is quite easy with Lisp. So as you know, factorial. What is a factorial? It's, let's say, the factorial of 7 is 1 times 2 times 3 times 4 times 5 times 6 times 7, right? So this is how to calculate that using Lisp. Another example of the 80s is SOAR. This is an attempt to create a general intelligence. So what they did here is basically create a whole architecture. And of course, this is still an ongoing project. So, we've they have added more modern methods and stuff like that to it. So basically, they tried to create a system where it has memory and short-term memory, and then it applies artificial, like machine learning algorithms to its long-term memory. For example, semantic memory is a way to have like structures. It's kept there for long term. Or episodic memory, it keeps specific images of what it sees, and then you can go back through episodes, right, and see what it did, how it interacted in the past, etc. In the 90s, we've had the advent of neural networks. Of course, the neural networks were still theoretical, and there were algorithms back in the 50s and 80s. But, of course, in the 90s, it's where exactly it started popping out, right? How did the neural network start? Where it's based, basically? Again, it's based on logic. And let's examine this philosopher here of the 18th century, David Hume. So David Hume had this thought of induction. So he divided into strong induction and weak induction. Let's say that all observed ducks are white, therefore all ducks are white. That's a strong induction. Or a weak induction is, I always eat with my left hand, therefore everyone eats with their left hand. As you can see, that the strong induction implies that there are a lot of data sets, because we see a lot of ducks, they're white. Then we have this assumption. However, the weak induction is that I only see myself doing this. So I assume then that everybody else is doing that, but it's not true. So as you can see, that neural networks are based on data, right? Machine learning is based on data. So it's based on this philosophy, really. So we see a lot of data, and then we make an assumption about this. And connectionism is is, of course, the whole theory behind neural networks, how everything is interconnected and they interact with each other, one neuron with another neuron, basically. So why in the 90s? Because computers started becoming more powerful. There was more computational power, not the same computational power as today, but enough to be able to create these algorithms. This is an example of the perceptron. This is the simplest neural network. We have like a set of inputs to have a set of weights applied. Basically, it's like a mathematical. This is a mathematical function where we have weights, etc. So it adjusts the weights and creates an output. And then if the output is not correct, then it goes back and adjusts the weights again until it finds the correct response. So this example here is a classification problem, which of course you could use neural networks or other algorithms to do. So what exactly a classification problem is? Let's say we have two different classes. One is a cat and one is a dog, right? As you can see, there are different examples. And then you basically are able to distinguish with a mathematical function, right? With a line here, based, let's say, on two features, the size and domestication, which is a cat and which is a dog. And then you can have more complex classification problems like this. In this case, you can't really draw a line and distinguish between the blue and the red class. So how exactly do you classify this specific problem? What you do is called dimension increase. So you use like mathematical functions and you increase its 2-dimension into 3 dimensions. And as you can see now, you can draw a line easily and distinguish between the two classes. This is like a trick of how exactly they do, and the importance of mathematics and, of course, machine learning and artificial intelligence. So machine learning, neural networks are a part of machine learning, basically. Machine learning, of course, we have different paradigms. The most important paradigms are these stated here: supervised learning, unsupervised learning, and reinforcement learning. Semi-supervised learning is not really the main paradigm. But what exactly are these? So these are based on the data that we have. So supervised learning, we have a set of data and a set of outputs. So let's say that we have a bunch of images of cats and dogs, and we specify that which images are cats and dogs. This is what we call supervised learning, because the computer knows, the algorithm knows what type of inputs and what type of outputs we're expecting. So what we do basically is we train the algorithm. So the weights are adjusted, as I spoke earlier about the weights, with the train set. And then after training it with a train set, then on the test set, let's say, we're able to accurately predict if that's a cat or a dog. Unsupervised learning, of course, is, as you understand, we only have inputs and we do not specify if it's a cat or a dog, let's say. And based on of course, this problem cannot be applied to cats and dogs, but it's able to distinguish, let's say, the different features of the image, and eventually be able to see, okay, the cat is actually different from a dog. So eventually it will be able to predict that, okay, this cat, these are the cats and these are the dogs, let's say. And this is also used for cluster analysis, basically clustering the data and seeing how far each other the data is from each other. If you imagine like a 2D space, and the more far they are, the less relationship they have with each other. So then they can be divided into different classes, let's say. And reinforcement learning is when you basically penalize the algorithm, and basically when it gives an output and it's not correct, then you say, okay, this is not correct. You add a penal value, and then it goes back and tries to add again, to calculate again everything. And for example, modern algorithms that let's say play chess or play any arcade game, let's say they started playing Mario or stuff like the Mario Kart and stuff like that. This uses reinforcement learning, basically, because the algorithm plays the game, and then if it does a mistake, it goes back and changes something and plays it again and again until it perfectly is able to play the game, let's say. And these algorithms are really quite available now because we have so much computational power, and the graphical processing units that we use are very parallelized, so this can be done quite fast. So let's look at more advanced neural network algorithms. Let's say we have the multi-layer perceptron. So in this case, we have more layers and more weights, more functions in between the input layer and the output layer. And a multi-layer perceptron, as you can see, every neuron is interconnected with every neuron in the next layer. This is what we call a multi-layer perceptron, or a recurrent neural network, for example, which, as you can see, the neurons are interconnected with each other as well, and they go back on a feedback loop. And this is an example of, let's say, an algorithm called long short-term memory, because theoretically, they can keep like a memory of their inputs and outputs, because the input goes back into the neuron, let's say. So you can say that they have like a short-term memory. Another example is convolutional neural networks, which is used mostly for image processing. In this case, they go through layers of different filters, convolution filters, max pooling, which is like a reduction of dimensions, and then they go through a network, and we have output. So let's say that we have an image of a 4, and then we have the algorithm then would actually be able to predict that it's a 4. We understand that every time it sees a 4, it would say, okay, this is a 4. Other models and simpler machine learning algorithms, such as support vector machines. This first graph is an example. Let's say we have two different classes, and the support vectors are basically these lines, and that we have a plane here. So now it's able to divide, instead of having just a simple line and saying this, we can actually add more accuracy by creating a plane here, as you can see. Decision trees, this is an example of a decision tree. Basically, we have a lot of trees, and they have different thresholds, and they go up into a specific length, and then there's a prediction about what happens there. For example, if this value is greater than 50, then if this value is greater than 30, then if this value is greater than something else, and blah 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 blah, and then it goes up to an output. Also, we have like Bayesian and regression models, more statistical. Bayesian, of course, is like probabilistic. Anyways, you understand. And regression, of course, is very important with statistics. This is an example of regression. As you can see, the relationship between every part. Basically, we have the closest it is, right? The more close of a relationship it has with the data with itself. So let's say we draw a line here, and this means that we're able to predict, close to the relationship of all the data. And then ensemble models, of course, are basically the same thing. They use all of these or some of these together to make a prediction. Let's say we can use support vector machines alongside some other model, let's say decision trees or something like that. So a lot of stuff have increased in accuracy due to deep learning. So deep learning basically is it uses the same models that we just saw, but it utilizes the fact that we have so much computational power today that we could really add a lot of layers in between and get really great results. So in this example, models could include like long short-term memory or convolutional neural networks or recurrent neural networks, and they have like a lot of layers, and they go up to an output. And what modern researchers have been doing is just applying these models to different problems, and all the time this is what happens basically. And then again, they might change the parameters and get different results, and then this is what drives the whole thing in the future. But no real development apart from this. We're just applying the same things over and over, but changing the parameters. There are a lot of problems when it comes to machine learning and neural networks. The first one, of course, is data quality. We have to have good data. They have to be processed in order for the algorithm to be able to get them accordingly as inputs, normalized, etc. I will show you an example later of this. Model tuning, different models have different parameters, different equations that they have. So you have to specifically choose like activation functions and stuff like that. Then interpretation of the model. Of course, you have the output. What happens then, right? We have to be able to interpret the model and see if the results are good or not. Then there's bias. This goes hand in hand with data quality. Let's say I give it images of cats and dogs, but 90% of the images are cats. Then it would have an issue predicting dogs because most of them are cats. So then it would mostly predict cats. That's a bias. Overfitting, again, it's like overfitting to the data. Let's say we talk about cats again. It starts mostly predicting cats. Why is this? Because let's say that the not because of the data itself, but the model tuning. Basically, this is what causes overfitting, and then you have to actually pick the correct model. Because, for example, perceptrons are prone to overfitting, so then you have to change the model and use something else. Underfitting is, of course, the opposite. So we don't have a lot of data, so the model actually underfits, and we have an issue here. Then we have generalization, right? The model has to be able to apply to a lot of different images that it hasn't seen, so or a lot of different problems that it hasn't seen. So we use the train and test data, of course, but then if we give it something completely different, it should accurately predict this or not. And like I showed you before, nonlinearity or other problems there, like I showed you with the classification problems, we have to increase the dimension. That's a neat trick. It's called the kernel trick. And then the model is accurately classifying data. Picking the right model, like I said, you have to pick the correct model. Parallelization is the hardware. It has to be, let's say, graphical processing units are much faster. So this is very important. Ethical interpretations. Data, of course, can be anything, right? So we have to consider the ethical repercussions of processing data. Let's say that we're actually processing someone's personal chat. We want to create something with that, make an analysis of his emotions, etc. Let's say, and that's a bad ethical approach, because you wouldn't want someone to use your personal chats to say if you're sad or not, let's say. And then comes to data breaching, of course. We shouldn't get data that we're not allowed to use, basically, based on that. So I have 6 minutes to show you a very simple example. This is predicting housing market prices. So let's say that we have a lot of data about houses. This is specific data is in California, and we want to predict how much each house would cost, right, in the market. So we have different information like the longitude, the latitude of the house, how old the median age of the house, how many rooms it has, the total bedrooms, the population of the block, households, median income of the people around there, and median house value, let's say, around there, and then how far they are from the ocean, because we're talking about California. I think it's Los Angeles, actually. So we have this is like an analysis of the data itself. As you can see, the median income here is not in dollars; it's like some other value. So we have to. This is a problem. For example, we have to normalize the data, or translate this number into dollars, or just translate everything else into this value here. And as you can see here, the median age is capped at 50. So this is like a histogram, right? So how many houses are that are over 50 years old, and everything is here because we don't have data around here after 50 years. So then we could either crop this and disregard it completely, of course. And here's another example that let's say the houses that are closest to the sea, to the beach, are more expensive than other houses. Yeah, this is California, not Los Angeles. Everything. So a simple model created is the random forest regressor. So what is this exactly? It's a bunch of decision trees, a lot of decision trees, and randomly, distributed. And the model, imagine that the model changes the trees all the time, and eventually gets to an accurate prediction. So what the first thing we do is divide the data into training and test set, 70-30. Let's say 70% of the data is the training set, and 30% of the data is the test set. And remember, we're trying to predict the housing prices. So after training, let's say this model, we have how do we evaluate this? So one way is to use the mean square error. So this is the error that the machine learning algorithm predicts. What is the error? The margin of error, let's say. So this is just a number, right? So we can't really understand what this means. But if you take the square root of this model, you can actually see that it's 261. So this means that our model is actually predicting with an error of $261 how close the price of the market is. Then we use this library here with the SHAP. This is like a model, a way to evaluate basically the model's accuracy. And as you can see, one moment. Yeah, as you can see here, this is like a graph of the most important features. The most important feature is the median income, and then the latitude, longitude, and the house median age. So these are the most important features that contribute to the price changes. And then here we have other graphs that say, if the model is driving the price up, if this feature is driving the price up or down. And same goes with latitude and longitude and house median age. And then this is a comparison of the median income and the house median age, basically. So yeah, that's just a simple example, basically. So what is the future here? Are we going through a new AI winter because there's no real breakthrough when it comes to new research? We're just reusing what we know, and we're just going forward. Then we have quantum computing. Is that going to increase the power of machine learning algorithms, perhaps maybe increase something else, the results of the models? Then are GPUs going to contribute more? What's going on there? As you know, the prices of GPUs have increased the past year. And then Moore's law. This is no longer a law. Basically, this stipulates that every 2 years the number of transistors in a processing unit double, but this is no longer the case because, of course, of size. We can't really go down to more than, I don't know, some nanometers of transistors. So what exactly is the future here? So that's all. Thanks for watching.